Hello, everyone. My name is Gustavo Silva, and well, it's my first time in Sweden, and of course, it's my first time presenting at this conference too. And thanks to the organizers for the invitation. Um, Today, we are going to be talking about the challenges and innovations of towards safer, flexible arrays in the Linux kernel. Before I begin, I have to say that my work in the kernel community has always been supported by the Linux Foundation, and recently by Alpha Omega, the Alpha Omega project. So, okay, well, a couple of words about me. I've been doing upstream kernel development for 8 years, mostly focused on security. I am part of the kernel self-protection project, which is basically the Linux kernel division of the Google open source security team. And well, this is the agenda. We are going to start by explaining a couple of simple concepts that we are going to use throughout the whole presentation. Then we are going to move to the main part of the presentation, where I'm going to be exploring the topic of hardening main copy, the addition of a new compiler option, strict flex arrays. We have a new attribute, counted by. And also, we are going to touch a little bit about a building compiler function, which is building dynamic object size. And well, at the end, some bleeding edge kernel hardening, something I've been working on for the last couple of months. Okay, let me start with this pretty simple code. What we have here is, well, we are declaring a structure that we are naming trailing, and merely to illustrate what a trailing array is. So a trailing array is merely an array that is going to be declared at the end of a structure. Something important to notice here is that the size of the trailing array is clearly well defined at compile time, right? So let's keep that in mind. Okay, now flexible arrays and flexible structures. Well, a flexible array is merely a trailing array that is going to be used as a variable length object. This is, its size is not going to be defined at declaration, it's going to be determined at runtime. And a flexible structure, well, is merely a structure that contains a flexible array. Flexible array members were introduced to the C language in C99 as a proper way to declare a flexible array in a structure. One of the requirements for the use of a flexible array member is that they should be included in a structure together with another member. In this case, usually when we declare a flexible structure, that other member, well, one of those other members is going to be a counter member. This counter member is going to be used to hold the total number of items or elements our array is going to have at runtime. And well, we have a new attribute, counted by. We are going to get into the details about how this attribute came to be. But just for now, I want to tell you that if you happen to be working on a code base that need to use a flexible structure, this is how you should be declaring your flexible structures from now on. So we're going to get into the details of counted by, because, well, it's our new baby in the kernel self-protection project. We are going to see why we love it so much. Here's an example of the use of how we would use a flexible structure. Usually, well, we are going to do some arithmetic to calculate the total size to allocate for the structure together with the flexible array member. So in this case, well, we're getting the size of the structure plus the size of the element type, and multiply for a number of members that our flexible array is going to have at runtime. And well, the recommended way in the kernel, in the Linux kernel, is instead of using open-coded arithmetic, as in this case, instead make use of the struct size helper. Okay, well, you might be wondering, okay, but before C99, how we were declaring these types of objects, how we were declaring variable length objects. Well, the answer is that originally, when people wanted to declare a flexible array member, they would use a one-element array. That's the ancient way of doing that. And the old way is using a zero-length array. We consider the one-element arrays a bogey hack. And here is how we would calculate the size for the allocation. You might infer for this part of the code why that is a bogey hack. We are not going to get into the details of this because, we have just 30 minutes for the presentation. And well, this is how you would allocate the size for a structure that contains a zero-length array. And well, zero-length arrays were introduced as a GNU extension in C90, sort of like as a remediation for the lack of a proper way of declaring these sorts of objects. So people didn't want to use one-element arrays anymore, so we had zero-length arrays instead. However, the Linux kernel was polluted with one-element arrays and zero-length arrays. But this have been changing over the last 5 years. At some point, while I was doing something else, I ran into this bug. Here, what I found is, as you can see, we have a zero-length array in the middle of a structure. And this commit, what it does is that it is adding a new member just after the zero-length array. The issue with this is that at runtime, this array is going to be used as a flexible array. So we would allocate some memory for this array. And at the moment some data is going to be written, well, we are going to overrun our RCU head. So that's a bug. That's undefined behavior. And the fix is simple. We just transform the zero-length array into a flexible array member and place it at the end of the structure. So with this simple change, with the change of placing the array at the end of the structure, the compiler is going to enforce this behavior. So the next time someone else comes and make the same mistake, well, they won't be able to build their code. And well, of course, they won't be able to submit their code. This bug was introduced in 2011, and I found it in 2019. It was an 8-year-old bug. And that was the kickoff of flexible array transformations in the kernel. So that was the moment when we realized the importance of looking for more of these issues in the kernel, but most importantly, to try to prevent them from happening in the first place. OK, now let's get into the hardening of main copy and strict flex arrays. This is a simplification of a fortified version of main copy. But before we get into the details, we all know that usually main copy cannot, this API is not able to sanity check either the size of our source object or our destination object. So if you want to, if you are a careful developer, you would add sanity checking before calling this function, right? So the idea of the fortified version of main copy is include the sanitization in the internals of the function, right? And well, we can do this through the enabling fortified source in the configuration file. And well, this is actually a past version of main copy. This is not the last version of main copy, but this is how I'm going to use this as example of how things have been evolving. So let's get into this example. Let's explore how we would use main copy and the effects of main copy while trying to write data from some source into a flexible array. In this case, a flexible array member. So, well, first, internally, main copy was using a built-in object size compiler function. So what this does is that it is going to retrieve the size of both the source and the destination object. And at compile time, we are going to compare those sizes against the number of bytes we want to read from the source and write into the destination object. However, in the case of flexible array members, built-in object size returns -1. The reason for this is because a flexible array member is an object of incomplete type. So let's remember that the type, part of the type of an object is its size. So at declaration, our flexible array clearly lacks a size. We just use empty square brackets. So yeah, it's an object of incomplete type. So in this case, what is going to happen first is that our destination size is going to be quite large number, quite large value. And of course, this condition will never be true. So the sanity check in this case is not possible. It is not possible to bounce checking the size of a flexible array member. This is expected behavior, again, because this array is an object of incomplete type. So this is, so far, this is okay. This is fine. Okay, but long story short, at some point, we noticed that building object size was returning -1 for any trailing array. And by any trailing array, let's remember our first piece of code, our trailing structure. In this case, well, the size of the trailing array is clearly well-defined at compile time. However, building object size cannot reason about the size of the object, even when the compiler has enough context to determine that size at compile time. So that was quite strange and a bit disappointed to find. So under this scenario, main copy is not able to sanity check any trailing array at all. So yeah, the hardening of main copy is ineffective in this case. But well, it might be worth asking, okay, but why? So I don't know, how many of you are familiar or have used building object size before? Great, one, okay. Okay, so any of you have any idea why of the behavior of building object size with any trailing array? Okay. There are historical reasons for this. This is a piece of BSD code. And what's important to notice here is that we have this structure, and at the end, we have a trailing array of 14 bytes. However, at runtime, this array is going to go all the way up to 255 bytes in size, right? So we have a trailing array of fixed size at compile time that is going to behave as a variable length object at runtime. So at some point, compiler people realized that there were a lot of legacy code that were using this kind of code constructs. So they decided actually not make a distinction between any trailing array. So they assumed that if you were to use a trailing array in your code, at some point at runtime, you would probably would like to use that as a variable length object. So that's the reason why the behavior of building object size, and also this affects the behavior of this other building function. And we are going to get into these details. So yeah, in this case, what do we do? Is the next sensible question. So there are a couple of things that we could do. First, well, we should fix the compiler side, right? We should try to fix building object size. And there are a number of different things that we could do at the same time. One is, as I said, fixing building object size. Also, it would be useful to get rid of unambiguous ways of declaring flexible array members. Let's remember that before C99, people were using one-element arrays and zero-length arrays. And the kernel code was full of those declarations. So that's the work of flexible array transformations that we've been doing over the past 5 years. We've been transforming one-element arrays and zero-length arrays into C99 flexible array members. And well, another thing that we could do is, well, to promote, to try to convince compiler developers of implementing a new compiler option. This new compiler option would enforce the use of only C99 flexible array members as objects of variable length at runtime, or as the only way to declare a flexible array. With that, they would help us to enforce not having ambiguous ways of declaring the same type of object. And at this moment is when we decided to name one-element arrays and zero-length arrays fake flexible arrays as a way to distinguish them from what we call a true flexible array, which is a C99 flexible array member. Okay, so now we only want to use flexible array members as to declare flexible arrays, okay? So let's see how this compiler option works. This compiler option was released in GCC 13 and in Clang 16. And how this works is like this. This is the strictest level value that we could use with this compiler option. When we use strict flex arrays equal 3, the compiler is going to treat C99 flexible array members as variable length objects. So any other type of object, if you declare a one-element array or a zero-length array and you try to use that as a flexible array member at runtime, the compiler is going to assume that that is not your intention and that you actually wanted to use that array either as a one-element array or as a zero-length array. So in this case, well, flexible, if we use building object size to get the size of a flexible array member, we would get -1, and that's okay. That's expected. And for the rest of the cases, of course, including one-element arrays and zero-length arrays, we will get the actual size of the object at compile time, right? So in the case of a one-element array, well, it's the same as applying the size of operator to the one element. In the case of the zero-length array, well, we are going to get 0, right? And well, with this option, with this compiler option, we gained bounce checking on all trailing arrays of fixed size. So we are fixing issues. Well, we are fixing the problem that we originally had. This compiler option was enabled in Linux 6.5, so that was really a great accomplishment from on the kernel self-protection project. Well, now the ambiguity of trailing arrays is gone when this compiler option is enabled, and after transforming a huge amount of one-element arrays and zero-length arrays. And well, with this, we've gained bounce checking on trailing arrays of fixed size, as I already said, right? Okay, but what about flexible array members? It would be great if we could sanity check those arrays too, which at the moment, we only get -1 from building object size. So, well, in this case, that's when the counted by attribute come into play. Here's how this works. We would annotate a flexible array member using this counted by attribute, and the member in the same structure that we know at runtime is going to hold the total number of items the array is going to have, right? So if we do this, well, actually, this is coming in GCC 15. GCC 14 was just released like some weeks ago, and this is already work in progress in GCC 15. In Clang, this is already out, so this is a reality right now. So you can use Clang 18, and you can start using in your code this counted by attribute. And this is kernel code. Before it was released in Clang 18, we were already doing counted by annotations. So Case Cook and I have been annotating code with this attribute for months. And well, this is how it works. As I was saying, this is a way to connect that member in our structure that is going to contain the total number of items that our flexible array member is going to have at runtime, so that it will give context to things like array bound sanitizer and a built-in dynamic object size. So when we annotate a flexible array member with this attribute, now this built-in compiler function is going to know, or is going to be able to instrument kernel code. In our runtime, we are going to be able to sanity check these types of objects. And well, again, this is this is the bounded version of a flexible structure. So this is how you should be coding your flexible structures from now on. And well, before we continue, a quick recap. So we enable strict flex arrays 3, and with that, we prevent the ambiguity of having multiple different ways to declare a flexible array or a variable length object. With counted by gives accurate context to things like sanitized bounds and to building dynamic object size. So probably all of you know that under config UBSAM bounds, what we actually use is F-sanitized bounds, right? Okay, so now let's talk a little bit about building dynamic object size. So I was saying that a previous version of main copy was using building object size. So with the addition of the counted by attribute, now we have replaced the building object size compiler function with building dynamic object size. And with this, we are gaining coverage at runtime. And well, if you enable config fortify source, you are going to get all these benefits. Okay, now let's get into some bleeding edge upstream kernel hardening. This is something I've been working on over the past a couple of months. And this has to do with a new compiler option that is coming, this has been released in GCC 14 too. So you can also make use of this compiler option. How this works is this. Well, we want to detect these sorts of problems in the kernel or in any code base where we have a flexible structure and we have a composite structure that contains an object of the type of that flexible structure, but in the middle in the structure, you know? So this, again, is prone to undefined behavior issues. So we want to, if possible, we want to avoid at all costs this type of code constructs. So I built a kernel with this option enabled, and I got about 60,000 of these warnings in the upstream Linux kernel. Yeah, really. This happened on May last year, and I was working on other stuff, and I was helping Qin Xiao. Qin Xiao was the GCC developer who implemented this compiler option. So Case and I were helping her to test the code. And well, I built the kernel, and when I saw the number of warnings, I was like, oh my God. So I'll probably come back to this in a couple of years. So, but well, what's interesting is that about 1% of those warnings are unique warnings. So, but anyways, I mean, those are like quite a lot of warnings to resolve, right? Yeah. So then I started looking into the warnings and try to see if I could identify some patterns, like trying to classify the different type of code constructs that would cause these warnings. And I actually found 4 different cases. So the most simple, the easiest one is when the flexible array member is actually never used at all. This means that no code in the kernel is allocating memory for this array. So this is a simple one because we just need to remove the flexible array declaration. And with this commit, actually this is just part of the commit. I removed 4 of these instances of code, and I fixed 100 of these warnings. So that was really great. Okay, that's one case. That's the simplest one. That's the simplest one. The other case is when the flexible array member is never accessed, and only the rest of the members in the flexible structure are going to be used. Usually, when that is the case, is because the composite structure that is including an object of the type of the flexible structure, it only needs the header part of the flexible structure, right? So it's never going to use the flexible array member, right? Okay, so the solution for these warnings is, there are two possible solutions for this. One is to separate to have two different structures, two separate structures. Here I have the original flexible structure, and at the bottom I have another one which I just added the suffix HDR just to illustrate that it's a header structure. So in this case, I'm leaving out of the equation the flexible array, and I'm only going to include in this structure the rest of the members, right? So that's something simple to do. And then I would use the flexible structure header to declare that object in the middle. So originally, before we have this, our composite structure with our object of the type of a flexible structure, so we would have a flexible array member here in the middle. But with the previous change, creating two separate structures, I just use the header one, right? And I would fix the warnings with this solution. However, this solution is not always appealing for anyone. So usually, we don't want to duplicate stuff just for the sake of duplicating things or for fixing false positives. Because in this case, what we are fixing are false positives, right? So another solution is to use the struct group tag helper. The struct group is a family of helpers. I don't know if are you familiar, or any of you are familiar with this helper in the kernel, or have you used it? Yeah, great, awesome. Yeah, well, the history of this struct helper is interesting, but it's not part of the presentation. But if you want to know about it, you can ask me at the end. It's really interesting because, well, I'm not going to get into that. But yeah, believe me, it's really interesting. Anyways, so we have this family of helpers. And look at this. What we can do with these helpers is something magical. You know, we have our original structure. These are the header members of our flexible structure. And we enclose the header part in a tag structure. So with this, we don't have to duplicate. We don't have to create a entirely new structure. We could use the struct group tag helper, and then, you know, in our composite structure, we just can declare an object of the type of our header structure. You know, so let's see again. This is the before, and this is the after. You see? So that's another solution, and that's actually the solution that I am using. Okay, so that's case 2. And well, this is an example. This is a commit where I am doing that. We have our flexible structure. We use the struct group helper to group the rest of the members of the structure and leaving alone the flexible array member. And then, in the composite structure, I replace the declaration of an object of the type of a flexible structure with the declaration of an object of the type of our header, right? And with that, I'm fixing those issues, because now this compiler option is not seeing any flexible array member in the middle of this other structure because it just doesn't exist. Okay, and this is the case number 3. In this case, probably this is the most complicated one. What happens here is that sometimes when people use a flexible structure, sometimes they don't know exactly how big the structure is going to be under certain circumstances. But at times, they have an idea of how big this array is going to be. So for those cases, they would declare an array of fixed size following the object of the type of the flexible structure. And if you notice, the type of our array is the same type of the flexible array. The type of the fixed array is the same type, is of the same type of the flexible array member. So with this, we have an implicit union. We have here flex array and fixed array. They share the same memory address. So that's an implicit union. So this is an example of that type of issue. Here we have our flexible structure is digest data. and our flexible array member is diest, right? So we enclose all the members in the flexible structure into a new tag structure, and in the composite structure where we have our implicit union, we declare an object of the type or our tag structure, and we leave out of the equation the flexible array member. You see? That's the trick. However, in this case, in many of these cases, the code actually was going to try to access not the fixed array, but the flexible array member. And that's when things get complicated. So, well, again, the code is going to try to access this flexible array member, not our fixed size array, right? So that's a bit problematic because with this change, we don't have access anymore to our flexible array member, right? Okay, we can save the day through the use of container of. So I'm pretty sure that you are familiar with this macro, right? Okay, so we save the day through the use of container of because container of is going to allow us to get a pointer to the flexible structure. And through that pointer, we can get access to the flexible array member. And the compiler warning is gone at the same time. So that's the trick. And well, if you are curious, when I upload these slides, you can take a look at the code. And the last case is the same as case 3, but on the stack. And for that, we use a couple of other helpers. In this case, declare flex helper and the declare raw flex helper. This again is those changes, those patches are convoluted and are a bit problematic. So I didn't think that I was going to have enough time to go through this example. So I'm just showing here the commits, and you can take a look, right? Probably in another opportunity we can go through all of this in detail. Okay, so a lot of patches have landed in mainline recently. Well, actually, the merge window is currently open. And well, all of those patches that I have sent over the last 2 months, they landed in mainline. And with that, well, I've managed to fix about 30% of those unique warnings right now. And that accounts for like 20,000 of total warnings. And I sent like less than 20 patches. Okay, some conclusions. We have enabled strict flex arrays in the Linux kernel. That's already a reality. The counted by attribute is a reality right now. You can use this attribute if you use Clang 18, and it's coming in GCC 15. We replace building object size with building dynamic object size. With that, we gain coverage, bounce checking coverage at runtime. And well, gaining bounce checking on flexible array members, well, it's just around the corner. And well, Fortify source benefits from counted by, and UV sound bounce also benefits from these two. This is where I tell you that the creation of the struct group family of functions is interesting, because in part, thanks to the creation of those helpers, in the most recent version of a hardening of a main copy, I'm sorry, the last version of the fortified main copy, thanks to those changes, the vulnerabilities of the last years, I could say probably the last 6 years, could have been prevented. And well, we are finding a lot of bugs in the kernel and also in user space. Again, that's another story. Some people from Android have reported to me some issues with the flexible transformations that ended up uncovering bugs in user space. And well, we have a clear strategy to follow to address that daunting amount of warnings of flex array member not at end warnings. And well, the security of the kernel is being significantly improved over the last years. And I return back. Oh, well, with that, thank you.
At a time. I mailed with the keys in private about this, and I think my first comment was like, yeah, with this we have achieved feature parity with Algol 60 for arrays. Great, we are at 1960. But the other one was like, what we actually would really need at this point is a document in the kernel, like this is how you write flexible arrays.
Yes.
So like with good examples and say like, if you want to do this crazy thing, this is exactly how you should do it. Don't do it any other way. So
yeah, you're right.
If
yeah,
you
absolutely.
and Keys could like write, I will review it. So if you guys could just write the documentation of that, that would be great.
Yeah, absolutely. Yeah, absolutely. That's something that we should do. We are going to do that. Yeah, definitely. Thank you.
Yeah.
One question, is it totally safe to use multiple? You have these two cases where one was a fixed array and one was a flex array, but if you have many flex arrays in the same?
If you have multiple, like if you have, you mean if you have multiple flexible arrays in the same flexible structure?
Yeah.
Well, that's not possible. I mean, we would use a union for that.
So is the compiler will prevent that?
Yeah, it's going to complain. But you would use a union for that. Yeah.
Andreas is raising his hand, so I'm sure the Rust guys must love you with this. I mean, so one joke aside, one comment. If you can go back to that the struct group thing you had and the examples, this one is actually a nice one. Why go through all that when clearly the code is using a flexible array with a static array, so you don't need a flexible array. Just nuke the thing and use the digest here. Well, why all that? I mean, it seems like super complicated code for something that in the end is super simple and all statically assigned in that structure, because you have the array that is fixed size here.
No, yeah, you're right. And actually, I am researching those cases, and that's actually what happens with the case number 4. People realized what you say. They say, okay.
Yeah, and that one, by the way, another one. I mean, whoever declares an array on stack, he is really looking for trouble. So that should be like, please allocate no array on stack.
No, but we don't have actually. We are not declaring flexible arrays in the stack. This is preprocessor magic, let's say. So actually,
it's just bad declaration of an array, essentially.
Yeah.
A real array that you're going to malloc.
Sorry?
These cases are just simply bad declaration of an array that you're going to malloc. So not really flexible, just really a real array that you allocate memory for.
No, we are not. Well, we are not allocating dynamic memory. We are. That's a static. That's a stack memory. That's a space in the stack, right?
For these cases.
For these cases, yeah. Yeah, that's why.
But again, an array on stack is really asking for trouble in the first place. So.
No, but it's not a flexible array.
An array, whatever the array is on stack, is asking for trouble because you can blow the stack.
Okay, so you're saying that.
So I'm saying, yeah,
we shouldn't use
maybe you shouldn't do magic with flex array and ask for rewrite the code and allocate memory for your thing.
Oh, I get. So you're saying that we shouldn't use arrays in the stack at all?
No. Yeah, I think you shouldn't.
Yes or no?
No, you should not have an array on your stack. I mean, just use
that's
a pointer
what you're
and allocate.
That's what you are saying.
And that's my point here. You have these tricks or these plans for fixing your flexible arrays, but those arrays shouldn't, for that case, for these cases, for example, I think personally they shouldn't. And and people have complained to me in the past, don't put an array on the stack.
Yeah.
Just
I
allocate
mean,
them.
You're probably right.
And the other case before that, I thought, I mean, sure, that's going to work, but that makes the code fairly unreadable. And in the end, your array is not flexible at all here, so it's static. So why do all that? Isn't there like a simpler solution for fixing your warnings.
Yeah.
That was kind of my comment.
Yeah, probably. Yeah, probably there is. I mean, this is work in development, under development. So I'm actually researching and reading and trying to. I'm still working on this. So probably I'm going to find like a couple of other cases, and I'm going to find different solutions at the end, right? But so far, this is how we are addressing these issues. But yeah, absolutely. I mean, it could evolve and it could change over time. Yeah.
Okay.
Thanks.
I just want to put one quick comment. It's super nice fixing all of the problems that we have, but all of these problems go away. If you write your code in Rust, they simply cannot happen.
Yeah, rewrite everything in Rust to remove the warnings.
I agree, but I'm pretty sure that you have received the same answer, right? Like, I mean, upstream kernel development is nuanced, right?
I agree.
Yes.
We cannot make revolutionary changes overnight, so it has to be incremental. Because
Absolutely.
technically it's challenging, but also socially. So, yeah. But yeah, sure.
Yeah, well, I think one final question before we hit the break.
Over there.
Keyword first. Okay.
I would just like to, a very short comment on that discussion, that there could also be cases where you would want a flexible thing sometimes, in which case your solution is very good because it's flexible.
Yeah. No, actually, that's a good point because, after that question. Yeah.
Can I declare like the flex array as attribute and also use the union? And it will be cause some issues with the memory alignment when I try to use the container to access this union and also the flexible array through that.
I'm sorry, I didn't get the whole thing.
Sorry. Can I declare my flexible array as with the attribute to avoid padding, for example, in my memory, and declare my union with this flexible array, and should be any problem with that or not? It's okay.
Oh well, if you notice, these cases. Let me show you. You see the packet attribute here?
Oh yeah, I didn't see.
So with that,
yeah.
that is gone. That problem is gone. Yeah.
Okay, thanks.
Let's take a break then.
Thank you. Thank you. Thank you.